Okay, great. You guys are getting my presentation, right? Not the presenter mode. Okay, so today I'm going to talk about using data that we've collected on site to help inform our AR calculations. And so today's meant to be interactive, and so I'll ask questions. If you have questions, just interrupt me, or any comments, interrupt me. So last week we went over these 4 different types of data collecting equipment. So we had the thermal camera to find temperature data, and then also that emissivity data that comes with that. And so for that, the main ARs that will probably come from that is to insulate something, so it stops losing heat. And then the next piece of equipment we looked at was the ultrasonic leak detector. And so for that, our main AR is going to be to fix compressed air leaks. Then the third piece of equipment was the Flue Gas Analyzer. And from that data, we can come up with probably 4 or 5 different types of ARs from that data. So one of them is tuning the boiler. One of them is getting advanced boiler control, which kind of goes hand in hand with tuning. And then we can also maybe clean the boiler or just like upgrade the boiler to a higher efficiency model. And then the last piece is our hobo loggers. So those are our data loggers. And so from that, I think there's kind of an endless list of ARs that can come from that, depending on all the information we have and what we do with the data. Okay, so first, I'm just going to kind of walk through how I would go through doing an insulation AR given thermal camera data. And so if you have questions in this part, just let me know. But if you haven't taken heat transfer, this might be, I guess, kind of obscure, but I'll go through it and you can kind of walk yourself through these slides if you ever have to do this AR. So the first thing, I like to use this thermal circuit analogy. I think it makes the most sense. And so for the thermal circuit analogy, you can calculate heat loss if you find the resistance between 2 points. So one of our points is our measured point with our thermal camera. And then generally our other point is going to be the temperature of the air. And so if we can find what's called the thermal resistance between these 2 points, and we know this temperature difference, then we can find our heat loss in watts, this Q value. And so what's generally most involved in this calculation is finding this total resistance. So for 2 resistors in parallel, the total resistance is going to be this equation here. And that's the same as 1 over R convection plus 1 over R radiation inverted. So this is directly analogous to electrical resistors. And Dr. Powell has a YouTube video on this topic from his heat transfer class, which is good information to watch if you have questions about this. So say we measure like a really hot pipe that's uninsulated. From that hot pipe, heat loss is probably most likely or will occur from radiation, and then also free convection. So free convection is where you have like airflow that happens from this natural airflow that happens because the pipe is very hot. And so that's different than like forced convection. So if you have like a fan going over the pipe, you're going to have a different heat loss, just something to keep in mind, but probably more involved than you need to get for this calculation. And so I just have this one question, like, will one term dominate the other? Meaning will radiation or convection, like what are you generally going to lose more heat to? this is for anyone who wants to answer or give their thoughts.
Doesn't it depend on the temperature?
Yeah, exactly. So that was kind of what I wanted to like point out. So like very hot things. So radiation is temperature to the fourth. So it's going to be a lot higher at higher temperatures. So radiation is going to be dominating for higher temperatures. So that's just something to keep in mind. Okay, so now we have this thermal circuit analogy, and we want to go and try to find how much heat we're losing from this pipe or this wall or whatever we're thinking that we should insulate. So what we need to do is we need to go about finding these R values, these resistance values. So one of the main things we need is AS, which is the surface area. And so for a pipe, if we have the outside pipe dimensions, we can calculate the surface area just using geometry. If it's like an oven, hopefully we got some measurements while we're on site. So these are things just to keep in mind. And then I also just wanted to point out, if this surface area is small, that's going to make these terms be large. And so we're not going to be losing that much heat if we have small surface area. So when we're thinking about doing these ARs, I think it's important that we're thinking about something could be really hot, but it also needs to have a large surface area for it to generally be worth it, because otherwise it may not be losing that much heat in the first place. Okay, so then going to find these two resistance terms. So the first one I'll talk about is this resistance of radiation. And so this one I defined it a little differently than what you might see in like your typical heat transfer class. But if you define it so it's this 1 over H radiation, which is the radiation heat transfer coefficient, then it makes it easier to do this thermal circuit analogy. But it's still going to be the same as this T to the fourth minus T to the fourth that some of you have probably seen before. So calculating this term is really easy. So we have our emissivity value, which we measured. And if we didn't get a good measurement on that, we can also generally look up values for that. This is a constant value that we can look up. And then we have our measured temperature and then like a estimated temperature of the air. So if it's inside a building, like 70 degrees, so it would probably be a good estimate. And then the other term we're trying to find is our resistance to free convection. And so for that, we need this free convection heat transfer coefficient. And rather than kind of painfully going through how to find that, I recommend just using this link. And I have checked all these equations in that link with my heat transfer textbook. And that'll get you a good value for this free convection heat transfer coefficient. And so with that, we can just plug in this formula and we can find our heat loss that we're losing in this area without insulation. Okay, so now we want to calculate essentially what happens when we add insulation. So how much energy can we save if we add insulation? So now our thermal circuit changes a little bit. So now we have our measured temperature, which is like the outside of this pipe. And then we have our resistance coming from the insulation. So this is the piece that we add. And then we have a temperature value on the outside of the insulation. And then again, we probably still have this, probably still have heat radiating from the outside of the insulation, as well as some free convection from the outside of the insulation. And so when I've done this in the past, how I've thought about it is when you add the insulation, ideally you're going to make the temperature of the outside of the insulation small. So it's no longer going to be really radiating heat. So if you go up to a pipe that has insulation on it and you put your hand close to it, you shouldn't feel like heat radiating to your hand. And that's sort of the same. That's what we want to do with our AR. That's the goal, is we're no longer really radiating heat. And so I've used this approximation in the past, where now we have just two resistors in series. So we have our resistance from insulation and then our resistance from free convection. And the resistance from free convection depends on this temperature on the outside of the insulation. And so generally, we won't know this value because we haven't gotten a measurement on it. So sometimes you can just use a best guess of what that value might be. And then you can recalculate this R free convection. If we know what the outside temperature of the insulation is, say maybe they have insulation on another pipe, and we just got a measurement on that. So we had a measurement of a pipe without insulation and then a measurement of the same pipe with insulation. Then we'd be able to use this thermal circuit analogy, and all we would have to do is calculate this R of the insulation. And then that R of the insulation would be our R total. And then we just take this delta T and find our heat loss. I think this is maybe less common because the AR is that we're recommending that they provide insulation. So the assumption is they don't have it already. So the next step is to find the thermal resistance from the insulation. And so that brings us to insulation R values. And so I've been talking about thermal resistance. And then if you go to insulation vendors, they come in the form of these R values, which are different than how I've defined them and how I've been talking about them in this presentation. And so I find that to be pretty confusing. And so generally, these R values on the insulation, like data sheets that you'd find at like Home Depot, they don't have any units. In the US, there are units of feet squared times degrees in Fahrenheit times hours over BTU. But there's different R values in different countries too. And so, yeah, so I think the whole thing has been confusing to me when I've done this. And so I think the easiest thing to do is to get this R value of an insulation type that you're trying to recommend. And then you want to back calculate K, which is the thermal conductivity of the material. And so to do that, first I would maybe change these units to something more friendly, like SI units, not necessary, but that's typically what I would do. And then if you divide by the width of the insulation, you can get back to your K value, the thermal conductivity of the material. And so once you have your thermal conductivity of the material, then you can use it to find the R value of insulation. And so the R value of the insulation is going to change for different geometries. So if you have just a wall, your R value is just going to be the K value of your insulation, your thickness of your insulation divided by your K value of insulation. So that is the R value that's reported on like the insulation data sheet. But for a pipe, that's not the case. For pipe geometry, you have to use this like natural log of the two radiuses over the 2 pi, then times the thermal conductivity of the insulation, and then times the length of the pipe. So all that to say is I would try to target finding the thermal conductivity of the insulation that you suggest rather than going off the like R value on the product. So once you have an insulation value, and R insulation value, you can just go back and you can plug it in here to your R total, and then you can find your Q again. And so that would be the Q that you lose with insulation, which should be drastically less than without insulation. And then you can find your total heat loss from the pipe, and then energy savings from that.
Jake?
So, yeah.
Is there really not a way of finding the K value with the R value? Because sometimes, I mean, if we have the R value, which is really used here in the US, it would be really useful to get the K value if we could.
Yeah. So you should be able to divide by the width of the insulation to get it. Any other questions or comments? That was kind of my wrap up of doing these installation ARs. Okay, no one has anything. I'll move on. Okay, so the next piece of equipment that we talked about was the ultrasonic leak detector. And so RT went through how to use that last week and how to pick up air leaks and how to use the app to document all the air leaks. So now we're starting from a point where we have all of our leaks documented in the app, as well as estimated pressure at all those leak points. I don't know how much we got into the pressure part of it, but the most accurate results will come from accurate pressure readings. But it's kind of impossible to know what the pressure is at the exact leak site. So I think often we use just the system pressure. I guess it's probably most accurate to use lower than the system pressure. If we had like a reading after the compressor dryers, I think that would be a good reading for pressure. Or if you're on site and you see like a gauge near the place that you found the leak, that would be the most accurate. But I think typically we probably use maybe 10 PSI less than the system pressure. And I think that's a pretty good estimate. So we've got our decibel readings and then our pressure readings from each of the leaks, and they're all in this app. So now, ultimately, we want these decimal readings from our ultrasonic leak detector to inform us of CFM loss, or cubic feet per minute of air loss in the system. And so to do that, I would just recommend using this leak loss template, which is here. And so this, let's see. Are you guys getting my Excel? Okay, great. So
Yeah.
This is the leak loss template. So ultimately, it will just interpolate a decibel reading from our leak detector and then a pressure, and then it'll calculate a CFM loss for us. So all these are at 115 PSI, and then these are like our different leaks from our app, or if you didn't use the app, just where you wrote them down. And so from that, we can get our total CFM loss from our leaks. And then I just added this today. This is from RT, I think made this. If not, I took it from one of RT's spreadsheets. But this little table here will then extrapolate to the full facility if we were only able to do, so like this is 75% of the area not covered. So ultimately you just need to change. So if you estimated that you did 25%, you audited 25% of the compressed air lines, then we have like a system to extrapolate how many other leaks we might find if we did the full facility. And then we would use this number for total CFM loss for calculations moving forward. Sammy, you got a question?
Yeah, just had a quick question. Do you know where the source for that conversion table is, or where it comes from?
I don't off the top of my head. I know there's a bunch of hidden cells in here, and I think it might be in there somewhere. I don't actually know that. I think Conrad made this sheet. I was trying to find that earlier, but that is a good thing that I think should be added to this spreadsheet.
Ultimately, Jake, it's actually from the manufacturer of the device. So
Oh, okay.
I can follow up and with you on that to get that documented.
Okay, perfect. Okay, yeah, so I think this template is super handy and what we should be using in our reports. I know you can also generate a report from the app that you enter in all your data. And we were looking at that today, and it doesn't give you the same results as this table. And I think that might be because that app is for maybe a slightly different piece of equipment. I'm not sure why, but I think ultimately we want to use this template table to convert our decibel and our pressure to CFM loss. Okay, so ultimately all we're trying to do is find CFM loss, and then we're trying to calculate, okay, how much extra energy are we using due to this extra compressed air that we're making that's just being wasted. And so there's a lot of different ways that I've seen people go from CFM to kilowatt, like extra kilowatt hours. And so it all depends. Well, the first thing it depends on is the type of compressor that you have. So you'll want to make note of what kind of compressor are they using, and then what is their control strategy. And so oftentimes we see rotary screw compressors. Either, this is the most common thing I've seen, is the rotary screw compressors in the load unload control fashion, or a rotary screw compressor with a VFD on it. And so for the load unload, how I've thought about calculating the extra CFM, or the kilowatt hour, is to use the loaded power of the compressor. And then you generally on the data sheet, it will have how many CFM the compressor can generate at the loaded power. And so you can use that value to calculate, okay, if we're leaking this much compressed air, this is how much more time the compressor has to run to make up that extra CFM. And then similarly for a VFD compressor, we can look at the data sheet, and the data sheet will have a power percentage compared to CFM output of the compressor. So as you vary the motor speed, you're going to output a different amount of CFM. And so we could use that to look at, okay, what is our kilowatt of our compressor going to be ramped down to if we fix all these compressed air leaks. And then you can calculate the energy use from that by multiplying by the total hours that the compressor runs in a year. And then there's also all sorts of other compressor types and then control configurations. And so this NREL document on page 11 has a good formula that uses, they use like a compressed air type factor in the formula. So if you have a specific type of compressor, you can use this factor as well as the CFM that you calculated from the air leak audit to then calculate your energy savings. Does anybody have any questions on that? I know that was probably maybe a little confusing. I guess the main takeaway here is that for different types of compressors, your CFM to kilowatt hour saved is going to be different. So it's just important to make note of that and make sure that you're using an appropriate relation there. And then moving on. So there's two other ways that I found that we can also estimate our CFM loss in a compressed air system. So this would be the same thing as doing an air leak audit, except here we would be doing a different method to find how much CFM is lost in the system. Does anybody have any ideas of how we could do that potentially? Go for it, Sammy.
You can record, I mean, if they turn off the air compressors, you can record how long it takes for the system pressure to drop down.
That's a
or how
good one.
quickly it
That's
drops.
yeah, that's on my list. And there's so for that one of the parameters that we need to estimate is the total volume of the compressed air system. So like the size of the tank and then all the piping. And then if we had our pressure transducer hooked up, there's a way to estimate how much leakage you're having through the system. And then there's another one that I can think of. And it goes along the same line sort of as that.
Hey, Jake, I'll jump in with a question on the first one, just to follow up. This was
Yeah.
meant to be really easy. So the method that Sammy just described, is that an easy method or a hard method for our IAC assessments? Brooke, because I see you on my screen, I'm just going to ask, do you think that method is easy or hard?
That would be kind of difficult in case, if they're operating, you're like, hey, can you shut down your equipment? That's kind of might not get timing. So if you're like,
Great. It's very valid. And if you can do it, it's fantastic, but you have to time it right, obviously, according to the customer's operation. So I just wanted to jump in with that, Jake. Thank you, Brooke.
Yeah, I would say that one is just if maybe they shut down on the weekends and we have a pressure transducer logged, we could do it that way. And the next one is similar. If you can't have operations happening. So just to keep things moving along. The other one that I have seen is to do this load unload test. So if the facility shuts down operations on the weekend and their compressor is continually being loaded, meaning that it's providing air, then they're just turning the compressor on to basically blow it out through the leaks. So you can use the time that the compressor is loaded when there's no production to calculate, again, another CFM loss in the system. And so this link here has descriptions on how to do those other two processes. But those are, like Julie said, harder, and we probably won't run into those unless we're lucky. But that kind of feeds into our hobo logger analysis later. And I guess just one other note, if they are loading and unloading their compressors on the weekend and they're not in production, I think a better AR is just to shut off their compressors in the weekend.
Jake,
Yeah.
A type of compressor that I've seen in the past is a centrifugal compressor. And those, like, what I saw is that the one was like over 1,000 horsepower in size. And the problem I found when trying to find savings was that the rate of savings per CFM was really different to a rotary screw compressor. And you had to factor other things like the valve system it had, the inlet valve opening, the outlet valve, and those things as well. I think I found a resource that was like probably last year or even longer than that. But yeah, just something to point out that there are also like centrifugal compressors that might be a little bit more specific.
Yeah, I think that goes back to just being aware that going from CFM to kilowatt hour saved is not the same for every compressor and every compressor control type. And I've never dealt with that type of compressor, nor am I a compressor expert, so I don't know if I can say more than that. Okay, so moving on, we'll talk about now using data from the Flue Gas Analyzer. And so we took our measurement on site, and now we have this good data for the flue gas excess oxygen content and its temperature. And so one of the common ARs that we'll suggest is to tune the boiler, which means to adjust the air to fuel ratio. And Ellie talked about this last week, so I won't go into it a ton. But essentially, we're trying to have them tune the boiler so they get higher combustion efficiencies. And so we can use just this efficiency of the boiler formula, which is the heat that goes into the water over the heat that's coming from the combustion. And so that should be our overall boiler efficiency. And so we can break that down further. And so that should be our thermal efficiency. And so when I'm talking about thermal efficiency, I'm talking about how does the heat go into the water inside these, what typically we're looking at boiler. I guess this doesn't have to be for a boiler, it could be for any combustion process. But for this, for a boiler, you have like all these tubes and you have water either flowing in the tubes or over the tubes. And so the thermal efficiency is describing how much of that heat is able to get into the water that we're heating up. And then the combustion efficiency is different, and that's describing more of our chemical, like air to fuel ratio process. So for the boiler tuning AR, we'll have read out our temperature of our flue gas as well as our excess oxygen or excess air. And then that will give us a value of our combustion efficiency. And then that value is also on the Flue Gas Analyzer. And so here we'll have that ADA combustion or combustion efficiency. And so for boiler tuning, all we're suggesting is that they have someone come out and adjust air to fuel ratio so that they move maybe from this like 76% efficient into the range of like this 82 to 83. And so I think the easiest way to do this is just to use this table here from NREL to say, okay, what's our efficiency now of our boiler? And so to find the efficiency of the current boiler, you would take your combustion efficiency that you measure, and then you would take the thermal efficiency of the boiler, which can usually be found in the data sheet. And then you can find your total efficiency of the boiler. And then the next calculation would just be to use the better efficiency and to calculate the new boiler efficiency. And then from that, we can back calculate this Q burn for each of the cases. So how much are they burning without tuning, and then how much would they burn with tuning? And so you'll see savings from that. And so I think the one note I have here is that I think someone can correct me if I'm wrong here, but I think generally we want to go into this like column of 300 degrees Fahrenheit because you get this like relationship of if you have really high thermal efficiencies, you're going to have lower stat gas temperatures because all the heat is going into the water. And so I think for some boilers, you're never going to be able to reach this 200 degrees Fahrenheit column because of your thermal efficiency. So what I'm suggesting is to use somewhere in this 83 to 85% range, with 85 being the max end. Okay, so that's boiler tuning. And then the other thing we can suggest, which is essentially the same thing, except it's online tuning. I'm just calling it advanced boiler control. I think there's probably a better name for it. Feedback tuning with excess oxygen control. So that would be where we have an oxygen sensor in the stack gas line somewhere. And then we're measuring excess oxygen, and we're automatically adjusting the air to fuel ratio in real time so that we always have high combustion efficiencies. And I think the energy savings calculations will be pretty much the same on that one, but the implementation cost is going to be a lot more for this one. So just something to think about. This one is probably better for larger systems. You get more savings. Okay, so then the other two things from our flue gas analyzer measurements. So I think one of them that we could maybe suggest is to clean the boiler. And so if we have known efficiency of our boiler from the data sheet or what it should be, and then we measured a high combustion value. So the boiler's tuned, they have a high combustion efficiency. We know what their boiler efficiency should be, and then we can calculate this thermal efficiency. And so if this thermal efficiency is really bad, something we could recommend is that they clean their boiler. So if it's really scaled on the inside or something like that, then the heat is not going to be transferred to the water as well. So that's one thing that we can recommend. And then the other one indication of this is if the stack gas temperature is high, that would be meaning that heat isn't being effectively transferred into the water. And similarly, if the stack gas temperature is high, we could also just recommend that they get a more efficient boiler. So more efficient boilers will have higher thermal efficiencies. So one that we just did for one of our assessments, we recommended, I think it was the boiler they were using had a thermal efficiency of 80%, and we recommended one with like 95%. Okay, any questions on that? Otherwise, I'll go into the hobo logger data analysis. Okay.
One quick question, Jake.
Yeah.
How much percent improvement in the boiler efficiency is like justifies an AR?
Percent.
Just as an estimate or a rule of thumb.
I would do the calculation, I guess, and see how much monetary value you think can be saved, rather than go for a rule of thumb. But Julie, you look like you're going to talk. You might have a better answer than that.
Oh, I was gonna say even 1%, even 1 or 2% can work, Sammy. It really ultimately will depend on what you recommend for them to implement. The O2 trim, the automatic, basically real-time controls that Jake was just talking about, you're going to have more significant savings, like over 5% for sure. But these savings can be achieved simply by using some more regular manual adjustment, essentially. So they can be quite low cost.
Thanks.
Good question.
Okay, so this moving on to our last topic. So this is using our hobo loggers. So first I'm just going to go through how to download the data really quick using our two softwares. And then this is sort of the outline I think we should do with all of our data. So first we want to plot it and do some sanity checks. And then once it's plotted and we think our data is good and we think we got what we wanted, we're seeing good data after we do all these sanity checks, then I think it's time to manipulate and start kind of correlating the data. And I think a lot of times step 2 is neglected, or you move right into step 3. I think step 2, we definitely want to do step 2 and really think about step 2 and just making sure that the data makes sense to us, I guess. And then lastly, once we have this data kind of manipulated and we've done some correlations with it, then we want to use it in combination with just other data that we found on site to suggest different ARs. Okay, so this is just going to be a quick outline of how to download the data for the old loggers. So for that, we want to open the HoboWare software. Then we just plug in our logger with the USB port. And then we just hit this read out data button, which is in red here. And then that'll bring up this option to save the file. and just save it as a hobo file. And then once you hit save, it'll bring up this, this box, and you can just hit plot. And so once you hit plot, you'll get this screen. And so this screen will show a plot of the data that you have. And so this is a good opportunity to just quickly look over the data and see what it looks like. But I recommend always exporting it to Excel or Python, whatever. I think Excel is better, but whatever you want to do. And so to do that, you hit this little Excel button, and then you can save it as a CSV file and then open it up in Excel or import it and do something with Python. So for the Bluetooth loggers, now you have to open up Hobo Connect, which is the app. So you can do that on your computer or on your phone. And then you want to find the DL number of the logger. If you haven't connected to the logger before, I don't think it shows the DL number. So you might have to click on a couple of them to find the right one that you want. So just double click to connect, and then you'll get this option. You'll get this screen here, and then you want to hit this button, which is the readout data button. And so that will automatically export the data to your Hobo Link account. So if you haven't made a Hobo Link account, go do it. I think we talked about that. I think Blake talked about that. So make a Hobo Link account. And then now from the Hobo Connect app, we want to go to the Hobo Link website and log into your account. And then you go to data on the top, then this little sidebar here, and then export data will be another option. And then we can export the data directly. The sensor that you just uploaded the data, you have to give it some time because it goes into the cloud. It'll come up here, and then you can export the data. You can do it directly to an Excel format or to CSV format. Okay, so now we have our CSV data, or we have an Excel file. So the first thing we want to do is just start sanity checks. So I recommend just opening it up in Excel and then plotting the data. And so I think asking these questions is the first thing we should do. So does the data look as I might expect it to? You should be going in with maybe some expectation of what you think it should look like based on what the people at the facility have said. And then the next thing you want to look at, is it the right order of magnitude? So if we're logging amps, are we in the range of the amps that we think we should be at? And so just as a reminder, we can calculate an estimate for the amps by using the power in watts. So this will come from the motor nameplate horsepower. So we would convert our horsepower to watts, and then we divide that by our power factor, our voltage, and then our square root of 3 factor. And then, so this is a way to get an order of magnitude estimate for the amps. And so just as another heads up, this is also one way that you can make sure that you're using the right current transducer. So making sure before we put the logger on that we have a current transducer that's big enough to measure the amps. Another way we can do that is through the FLA on the motor nameplate. So the full load amps is another way to see what our order of magnitude is, and then also make sure that we're putting the right current transducer. Yeah, so I guess I kind of skipped 3 and 4, but was the current transducer big enough? So if it wasn't big enough, you should see this right away, meaning you should see the current transducer data maxed out. Like if you put a 50 amp current transducer on there and you're only reading 50 amps, and then maybe sometimes you read 0, like the equipment turns off, that's kind of a telltale sign that you maybe have bad data. Another thing to think about, is there a lot of variation in the data? And also just thinking about what is measurement noise and what is actual measured change. And so I would say, does everyone know what measurement noise would be?
Mhm.
Or any questions? I
Just-
think,
Would that be like just interference from nearby equipment or anything like that?
yeah, it's anything that's going to give us like kind of little like squigglies. Like we're never going to read 20 amps, 20.00 amps for the whole time. We might be, I would say measurement noise is generally plus or minus an amp, maybe less than that. So if your data is kind of hovering plus or minus an amp, and you have like a constant load, then you're just picking up measurement noise, and that's not, you're not necessarily like a measured change in the process. So understanding what's noise and then what's actual change, I think, is important as well. Okay, any questions on this kind of sanity check stuff? I think this is a really important part of the process. Or any comments, any other things that people have to add to this part? Right.
Yeah, one thing. So in that equation for the amps, usually we would be getting amps from the hoverware, and then we could convert those amps into watts using that equation as well, right? And that equation is considering a phase 3 motor, right?
It is, yeah. And so my point here was to go into pulling up your data and having an estimate of, maybe even before you look at your data, like what do you think you're going to see? And if it's way different, that's, maybe a red light. One thing could be, am I on the right? Did we mix up the loggers? Am I actually looking at the right piece of equipment? So just things like that. But yeah, then you can also calculate power from this with the amp data that we collected.
I think in the equation, we would usually, the power factor would be the power factor for the entire facility, right? Like as in the one we get from the bills, and then the square root of 3 is the approximation, because we usually would get this data from one of the cables connected to the system, right?
Yeah.
And then the square root of 3 would approximate it for the other two.
Yeah. And I forgot to mention the power factor. So yeah, the power factor is usually what we find on the bills. But even if you're just trying to do an order of magnitude or like a sanity check, I think you can just use 0.9. And this is just part of the sanity check, like back of the envelope. As well, the voltage, I think typically we see 480. I haven't mentioned that, but make sure you get the voltage of the equipment that we're measuring. Yeah, and it's already 5, so I'll try to wrap up pretty quickly here. Okay, so now we have data, we think it's good. And so we have it in Excel, we have it plotted, just kind of a quick like raw plot. So now I think the next thing is to do different things to manipulate and then correlate the data. So this is just kind of how I've been thinking about taking data and then using it to inform ARs. And so just the data alone is not going to be enough to recommend anything. We have to change it in some way or use it with something else to actually inform an AR. And so how can we manipulate AMP data that we collect? So I think the first thing we do a lot of times is we convert it to power draw in KW. So I think this is something that we'll probably do pretty much every time. So you can do that just by this formula, except you solve for P here. You can easily calculate equipment runtime. That's a good one to do. You can calculate energy use by essentially integrating your KW data And then I was going to kind of do a brainstorm here on other ways to manipulate the data. So if people have thoughts on things they've done that are helpful, just shout them out. I know we're already kind of late, so. Nobody? Okay, well,
For the correlation, I guess what I've done in the past is using MATLAB. You can do a polyfit. Right, there's a function called polyfit or something, and then it'll give you some coefficients for a regression line, and you can use that maybe.
what have you used that for? That wasn't exactly what I was referring to here, but
Okay, not in an assessment. It has been for a class. But if, yeah, I don't know. It's just a way in which I was able to correlate data.
I would say that
then,
falls probably more under manipulating the data, like you used it to make a line to fit it.
Yeah.
For correlating data, I was more talking about like things like, does the data trend with temperature? Does it trend with operating conditions? So like, if as temperature goes up, is this thing going up? Is it going down? And then like, does it trend with operating conditions? So like, it should be trending with operating conditions. And so if it's not trending with operating conditions, I think that's a good example of maybe where an AR could come in.
So would you just like say, like look at a plot and see if there's like positive correlation or negative correlation and use that, you know, to like say something from the data, or would you go as far as finding the R-squared value for the regression?
I just mean like saying something from the data, not like like regressing the data. I'm talking about like the data, you know, it should have a meaning corresponding to like the operating conditions ideally. But if, so say one example is like, if they're not operating, but your data is doing something, maybe they can turn off a piece of equipment, or maybe they're running when they don't need to be. That was kind of my way of generally talking about this, but maybe it was a little confusing.
Yeah, no, sorry. I see the word correlation used so much in statistics that I just like completely mixed everything together. Sorry.
Yeah, that's fine. But hopefully that kind of makes sense. I was trying to do this general, but as I'm talking about it, I think it might have been better to do like a specific data set. Okay, so I'll just move on. This will be sort of the last thing I talk about. So just other things to consider when we're on site and we're setting up these data loggers, make sure we get all the pertinent information. So a lot of times that's the pump nameplate or a fan nameplate. So then we can get like pump curves and fan curves and all the other information. We also want as much information about the process as we can. So flows, pressures, temperatures. I think a lot of times we don't get enough information. And so it's always better to have stuff that you may never use. And so if you're logging anything, I think it's really important to like just kind of take a step and think about, okay, I've logged this, but how am I going to use it for something? And if I use it for something, what else do I need? And I think this is a hard part of assessments, is just making sure we kind of take a second and think like, okay, what do I actually need? And I think just in general, talk to each other and ask about things that could be important to get. And if you don't know if it's important to get and you're right there, just write it down. It can't hurt. Yeah, that's all I have. Any overall questions or comments or anything?
Going once? Going twice? Thanks, Jake. Appreciate it.
Yep.
I think I'll wrap it up quickly for now, saying goodbye. And remember, next week we'll start at 4:30. Have a good week, everybody.